Discussion today. I want to talk about how you actually make use of the pumping lemma to actually answer questions about whether a language is regular or not. So here is our pumping lemma, and the pumping lemma for regular languages says, suppose that we know that L is a regular language, meaning it's recognized by a finite state automaton and described by some regular expression. Then there is some language-dependent constant n, and we won't necessarily know what that is. But there is some constant n, such that I can take any string that's in that language, as long as it's sufficiently long, meaning n or longer. So you can get away with, all kinds of stuff when you're just dealing with short strings. But for sufficiently long strings, any string in that language, L, can be broken into three parts, x, y, z. And the interesting thing about that way of breaking it up is that we will then be able to pump the middle part, y, in the sense that x, y to the kz will also be in L. So in essence, what we are doing is we are saying any string that is sufficiently long that is in L, I can split into a starting part, a repeatable part, and a finishing part. And having identified that repeatable part, I can repeat it any number of times, including 0, and still stay in the language L. Now, in a sense, this is a fundamental limitation on automata. It says something about the fact that although automata can capture a notion of looping, they can't capture perfectly general looping. And so if we can't find ways to basically divide this string into a starting part, an ending part, and a single looping part, then in essence it can't really be regular. It can't be recognized by those automata. Now there are some limitations on how we break this up into the three parts x, y, and z. Specifically, the repeating part y cannot be empty, and the length of x and y, the starting part and the repeatable part together, has to be less than or equal to our critical constant n, and that's why the n is relevant, becomes relevant for us here.